Okay, so I am going to start off by discussing propulsion for a rocket. So the way that the rocket is originally forced upwards is water being pushed out by the heavy pressure inside of the bottle. So our thrust equation is defined as the change in mass times the velocity of the water exiting. This can be described as density of water times area of the nozzle times velocity of the water. In order to solve for the velocity of the water, it's easiest to use this form of Bernoulli's equation. So you can substitute this in to get a thrust equation that is 2 times P minus PO, where PO is the atmospheric pressure, times the area of the nozzle. In order to find the pressure at any given time, it's easy to look at this equation. The pressure inside of the rocket is changing throughout time as more water and air is let out of the rocket. This, in turn, changes our thrust force. In order to determine the pressure at any given time, it's easy to use this equation. PV to the K equals P1 V1 to the K, where P1 and V1 are the pressure and volume initially inside the rocket. K is our constant defined as Cp over Cv. In the case of air, it's around 1.4. So, using this equation, we can get a function for pressure at any given time. This can then be plugged into the equation of changing volume. dV over dt equals A times the velocity of water exiting. So, we get this final equation right here, which finds us the change in velocity over time, as well as pressure over time, and our thrust force over time. By plugging these three equations into ODE 45 on MATLAB, you are able to get a function of thrust over time. We get a function that looks something like this. In the beginning, it starts at around 1 Newton, and over a period of a couple of seconds, goes down to 0, once all of the pressurized air and water has been let out.
So I'm going to talk about how we can use the thrust force that we found previously to actually model the navigation of our rocket. So as you can see here, I drew a basic free body diagram of what our rocket's motion would look like as it's flying. So we've got 3 key forces here. The first one is the force of thrust, which we found in the propulsion section. We have our force of gravity, and we have the force of drag that's acting on our rocket. So we can break these down using our Newton-Euler equations. So if we sum the forces in the x direction, we have the x component of the thrust force, and we have the x component of the drag force, which is equal to our acceleration in the x direction. If we break down our forces in the y direction, we have the y component of the thrust force, the y component of the drag force, and the gravitational force, which gives us our acceleration in the y direction. So to add a little bit more detail on the drag force, we found that it is, for a rocket, it's roughly equal to 1/2 CD ARV squared, where AR is the average cross-sectional area of your rocket, which you can calculate based on the dimensions of your bottle. CD is the coefficient of friction, which can be calculated similarly, and V is the velocity of your rocket. So naturally, drag force is only active if the rocket's actually moving. So using these equations, we can actually plug it into a MATLAB simulation and actually see how our rocket will fly based on like an ODE 45 simulation. So these are sort of the key equations that you can use for that. Now, moving on to our actual experimental, setup and results, we decided that we would keep our angle and the amount of water that we had in our bottle constant, just to be sure that we were really isolating the effects of the PSI. So we kept it at 45 degrees, we kept it at 650 milliliters, which is roughly 1/3 of the 2-liter bottle, and we tried it at 30 PSI, 40, 50, and 60 PSI. And what we found is at 30, I won't read out the numbers exactly, but we found our distances traveled, and it is fairly linear. It's not exact, but an R-squared of 0.96 is not too bad. A couple things to note, though, that we ran into were during our first test of 50 PSI, one of our fins fell off, and every trial after that was a little bit different than it would have been before, just because even though we reattached it, it's not going to be exactly the same. Another thing with the fins is as we're testing and with each consecutive trial, the fins get a little bit wetter, and as they get more damp, they get heavier and more flexible, which also degrades their performance because they're not as stiff when it comes to exerting that moment that course corrects the rocket. The second thing that made a big difference is the wind. We didn't really think about it until we saw it in a trial. And if you shoot when there's like a big wind that's going to a side, or there's a headwind or a tailwind, it actually makes a really big difference on how your rocket flies. Like we had one trial that instead of going straight, it was off by like 40 degrees just because of the wind. So that's another thing to take into account and try to avoid.
An actual test of our rocket resulted in it landing 49 feet from the target when we launched at a 45-degree angle and at a pressure of 60 psi. From the video, it can be seen that the rocket swerves in the air and did not follow a smooth forward trajectory. One reason was that at the exact moment when the rocket changed direction, a fin fell off. This showed that the fin could not provide an adequate stabilizing force, which affected the flight. Improvements that could have been made include placing a weight towards the front of the rocket to shift the center of mass forward and to reduce the effect the wind had on the flight. Additionally, better attachments of the fins that would be more sturdy would have increased stabilizing forces and allowed for a better path. Finally, calculations of the center of pressure were pretty approximate and calculated from the projected areas on each component. Adding weight in the nose cone would also decrease the distance between the center of mass and center of pressure, leading to a better flight that would be closer to predicted results.